Does somebody want to try test out talking to make sure I can actually hear you guys this time?
Testing, testing.
Awesome, I can actually hear you. That's great news. Perfect. Okay, before we get started with content, does anybody have any organizational questions that I can clarify with you as a class? Everything going okay with finding PowerPoints, getting set up on mastering A&P, figuring out when your lab is? The lab Brightspace, I believe, should now be open. I was told the 22nd, so hopefully you guys can see that now. Yes, maybe. Okay. I'm not hearing any no's. Oh, there my chat go. No no's in the chat. Okay, so hope that means everything's good. Okay. So today we're going to actually start talking about the content, aka what will actually be on the exam. And we're going to start out by talking about the physics of blood flow and pressure. So as you might guess, right, when we looked at that video on Wednesday, we were looking at how issues with regulation of blood pressure can create different symptoms, right? So in order to understand the relationship between pressure and different diseases and normal functioning of the body, we have to know a couple things about the physics of how blood flows through the cardiovascular system, which is reliant on differences in pressure. Okay. So we have a little warm-up question at the bottom asking us to think about what factors are going to be pushing blood through the vasculature and what we think can slow it down. So take a second to jot down a note and predict. I know some of you have done the Mastering A&P assignment already for chapter 14. That's due on Monday for those of you who haven't. So hopefully you guys already know the answer, but hopefully we're all thinking about, right? We ended A&P 1 thinking about the heart, thinking about how cardiac output sends pressure out through the system, right? Pressure that also gets stored in the walls of the aorta briefly, right? When the heart is relaxing. We're now also going to be thinking about the rest of the vasculature. So vasculature is just blood vessels, right? So we're going to be thinking about how resistance from the vasculature can slow down the blood in different organ systems. So for that, we kind of want to think intuitively about the idea of friction, right? Kind of the drag that happens pulling on the blood from the vessel walls. And we'll get to mathematically how we can understand that as well. Okay, so we're applying the laws of physics to our understanding of blood flow and pressure. We're going to start a little from the ground up because I know not a ton of people in this class have had physics. Okay. Here's a question that's kind of our overarching question here. So we're thinking about how blood is moving through the circulatory system. We're going to be thinking about physical parameters that we're going to track varying across the vasculature. So as we think about blood flow, we're also going to want to think about anatomical differences in our different blood vessels and how that affects the movement of blood. So hopefully by the end of this lecture, and definitely by the end of our next set of slides, we'll be able to relate anatomical differences, physical parameters in the vasculature to blood flow. Okay. So when we're thinking about these physical laws, we're going to be thinking about pressure gradients. We're going to be thinking about the concept of resistance. We're going to be relating pressure gradients and resistance to our systemic circulation. And I'm going to pull up a poll real quick. These questions should be super basic, but I want to make sure that we're all paying attention and that we all remember some basic things about gradients. So go ahead and answer these two questions. also always nice to have some practice questions, right? Before we get to our quizzes and before we get to the exam for sure. Okay, take another couple seconds and polling. Most people are in. Okay. Okay, so hopefully everybody can see the results. So the most popular answers here are correct, right? So when we're thinking about gradients, pressure gradients, chemical gradients, we're thinking about flow happening down a gradient. All right, so we talked about chemical gradients, electrochemical gradients in A&P1. Now we're thinking about pressure, and that's going to be true as we move into the respiratory system as well. So pressure gradients work the same way. Flow is going to happen down the gradient from areas of high pressure to areas of low pressure. Okay. The main source of pressure in the cardiovascular system is the heart, right? As it contracts, we build pressure in the chambers of the heart. That pressure then also gets stored in the aorta, but that really the source of the pressure is that heart contraction. Okay. So the cardiovascular system, when we're thinking about the vasculature part, is really just a connected system of tubes. So all the laws that govern flow of water through a tube, water through a pipe in your house, are going to be relevant to our understanding of the vasculature. So I'm going to take you back. All right, summer. We almost didn't get a summer this year, all stuck inside, but I'm sure you remember the concept of summer, right? You're outside, you're playing with a hose, you're a little kid, right? You pick up a hose, peer down it, right? Like this little boy, nothing's coming out. Now, if you wonder why no water is coming out of this hose, you can make a prediction, right? So if we have just this part of a picture, right, we just see the hose, we see that no water is coming out. We might think, oh, the reason there's no water is that the hose isn't on, right? So if the hose isn't on, right, you didn't turn the tap at the house, it means there's no pressure moving through this system, right? There's no water pressure coming from the house. So since there's no water and no water pressure at one end of the tube, there's no water coming out the other end of the tube. There's no pressure difference, and in this case, right, there's no water at all. But if we add on to this image, all right, say you have a sibling, I'm an older sibling, but some of you might be the tortured younger sibling, right? If we add a little information here, we see that the situation is a little different, right? So in this case, the reason water's not coming out isn't that there's no pressure, it's that we have a blockage, right? So we have a pressure difference, but the pressure is actually all building up, right, at that kink. And when we release that kink, intuitively, we know what's going to happen, right? Because it's probably happened to us, right? It's going to come exploding out the other end, right? When we allow flow to happen, we're going to have flow happening down that pressure gradient from where all the pressure is building up here in the kink of the hose, coming out the other end, which is currently in a state of low pressure, right? So we can almost think of this bend in the hose, this blockage, as really high resistance. And we'll get to that concept of resistance later as well. So our vasculatory system really does work just like a hose if it split out and then had to go back to its source. Okay. So speaking of that going back to its source part, the thing about our circulatory system is it's a closed loop, right? It's a closed system. We don't have things entering at random parts. We don't have stuff leaving at random parts. There is exchange at the capillaries, right, of, you know, salts, waste products, nutrients, but we don't really have substantial amounts of new fluid entering or leaving, right? Usually all our blood stays in the cardiovascular system. So this blood flow is going to be happening the same as liquid in a tube, but we are going to need to remember that all that flow is going to have to go back to the heart and then get pumped back to the system. So that's going to put some constraints on our understanding of blood flow. Okay. So the pressure that's creating movement through this system is the force exerted by the blood, specifically the force exerted by the cardiac output, right? That blood coming out of the heart. Our flow is happening down a gradient, right? So our flow is happening from the heart, from that area of high pressure, out to the rest of the body, where we're going to have areas of lower pressure, and especially returning to the heart, we're going to see that our lowest pressure is going to be in those great veins returning to the right atrium, right? So we're going to be thinking of the difference between the high pressure coming out when the left ventricle squeezes, when it contracts, to that low pressure as the vena cava sort of dribbles into the right atrium. We are going to be thinking about various factors that are resisting the flow of this liquid, because we're going to see in future that we can actually change the flow and the rate of flow to different organ systems as necessary. So we're going to see that being able to regulate this flow is important to function of the body. So whenever we talk about resistance, we're going to use this letter R. Right? When we think about pressure, we're using the letter P, but what we're actually interested in is pressure differences, not just pure pressure, right? But we're thinking about that gradient, the difference between high pressure and low pressure. So this triangle, that's delta. So delta P, that pressure difference, is really the driving force from the area of high pressure at the heart to that area of low pressure in those veins returning to the heart. Okay. So taken together, we can relate all these concepts together and we get this equation. So the flow of something is equal to the difference in pressure divided by the resistance. And we are going to relate this to things we can measure in the body at the end of this lecture. Just gonna annotate again, right? So flow, you're all writing this down, is equivalent to our difference in pressure divided by the resistance. Now, when it comes to exam time, I'm not really going to have you be calculating out specific numbers of like rates of flow and stuff like that. But I do actually recommend that you just memorize this equation. The reason for that is what we do want to be able to relate is changes in pressure, changes in resistance, and their effect on flow. And it's honestly a lot easier to just remember this one equation and then be able to say, okay, so if we increase resistance, right, we're dividing by a bigger number, so flow goes down, and so on, just drawing arrows and using sort of dummy numbers, right, little fake numbers. Easier to do that than to just flat out memorize tons and tons of facts about if resistance goes down, if resistance goes up, if pressure goes down, if pressure goes up. So that is my recommendation to you, is to just remember this equation to make your life a little easier. So we're thinking about pressure gradients because that's this first part of the equation, right? That delta P is going to be partially responsible for our flow. It's the main driver. It's just going to be divided by the resistance, right? But the source of that flow is the pressure gradient. The heart is creating this pressure gradient when it contracts for the bulk flow of blood through the cardiovascular system, setting the stage for circulation. And we have to maintain that gradient through the circulatory system if we want to maintain blood flow. So we are going to see differences in pressure all through the system. Now, one of the ways that's simpler to think about this than thinking about all your different named blood vessels immediately is to just think about how two connected columns of water with a pipe between them would behave. So that's what we're looking at here. And before we go through these slides, I'm going to just pull up a little simulation. Do you guys all see a little column of water with a faucet? Thumbs up. Yeah. Okay. So this is a little simulation of pressure. We got little pressure gauges here. I'm going to place one here at the bottom. I'm going to place one here at the top of the water, and place one at the top. Okay, so when we're thinking about these columns of water, we're going to see that the pressure at the bottom, right, is going to be related to how much water is above it. So as we watch this bottom gauge, as I add more water, right, as I add more water, that pressure down there is going up. This pressure is also going up, although it's less because there's less water kind of sitting on top of it, and so on. Okay, so that's how these columns are working. So when you see these images of columns comparing, that's kind of why we're comparing the difference in height of the columns in order to measure differences in pressure. Because if there's more water in this column, overall there's going to be more pressure, like that pressure at the bottom would be higher. And if we had a pressure gauge here and we had another one next to it and pressure gauge here, but there was less water sitting on top, that pressure would be lower. That may be obvious to some of you, but I like seeing things when we talk about them. Okay, so that's something to know as we go through these next couple of images. Okay, so here we have two columns of water. They're of different heights. So we could label them with different pressures, right? This taller column of water, more water sitting on this bottom water, water at the bottom of the tube. So we're going to write down a higher pressure, right? Here we have 100 millimeters of mercury as our pressure here. This smaller column, we're going to think of as 60 millimeters of mercury, right? So if we're thinking about the flow, when we allow water to flow from one column to the other, first we're going to note the direction, right? And we can think of this as a gradient. So we're going to move from high pressure to low pressure, right? Down this gradient towards the area of low pressure, away from the area of high pressure, right? So we see our flow going to the right. Here, we're going to start out just by knowing what that flow rate is, right? We're going to note down there's a pressure difference of 40 millimeters of mercury. There's a flow rate of 20 milliliters per minute. So now we're going to compare that to a couple different scenarios. So here we have two columns of water that are exactly the same. They have a tube between them, but because those columns of water are the same height, there's no delta P, there's no difference in pressure. So there's actually no flow happening, right? There's no difference in pressure to create a force on this water. There's no gradient, so we're not going to see any movement, right? And that should intuitively make sense, right? If we had flow going to the right here, we'd have this second tube of water getting taller and taller and taller, right? If you imagine this scenario in your mind, you know that that doesn't happen in real life. Now, the third thing might not be quite so obvious. In this scenario, what we've done is we've filled both columns higher, right? So we're comparing this really to scenario A. So we've almost completely filled this tube on the left. We've also filled this tube on the right some, right? So now we're at 200 millimeters of mercury compared to 160 millimeters of mercury. Now, what we can notice about this is that delta P, that difference in pressure, is 40 millimeters of mercury, which is the exact same difference in pressure as we had in this first scenario. When we look at the flow rate, if you were guessing, you might guess that, right, this left column is at 200 millimeters of mercury. That's really high. Our flow is going to be fast. But we'll note that the flow is actually exactly the same for this scenario C as for scenario A. The reason for that is it's not the absolute pressure that matters, right? It's not the absolute pressure that creates flow. I'm just gonna write this equation like over and over again, right? Our flow is not created by pressure itself, but by differences in pressure, right? So because this difference in pressure is the same, our flow is the same. Now, this is dependent on our resistance remaining the same as well. If we had a change to the resistance, we would see a change to flow. But that wouldn't be due to the fact that this column is higher and the pressure is higher, right? All we care about is the pressure difference between two locations. Okay, before we move forward, does that make sense so far? You can either call out questions or you can type them in the chat. Kind of can't see all your faces at once, so hands don't work great. Okay. So our pressure gradients are what is creating flow. When we relate that to the body, the place we're seeing this pressure gradient is we're seeing a pressure gradient across the systemic circuit. We're seeing a pressure gradient across the pulmonary circuit. So remember, we basically have two circuits that we're thinking about when we were thinking about the heart, right? First, we had our pulmonary circuit that takes blood from the right ventricle, sends it out through our pulmonary arteries out to the lungs to get oxygenated and back to the heart, but to the left atrium. Then we had our systemic circuit where we send blood out from the left ventricle out through all our organ systems, out to our pinky, out to our big toe, and then back. Do you see a question? Okay, I do see a question about how we would know the resistance, and we're going to get to that in a minute. That's a great question, and it's coming up, so I'll let you know. Okay, so we're just starting with the pressure part, but I promise we will get to all the parts of that equation. You may wish we didn't. Okay, so delta P is our pressure in the aorta minus the pressure in the vena cava if we're thinking about our systemic circuit, right? Because blood starts in the left ventricle, then we might measure in the aorta. Remember that mean arterial pressure is basically the average pressure in the aorta. The blood is coming back through the venous system and eventually dumping into the vena cava, big blood vessel going to the right side of the heart. So when we're calculating the difference in pressure for our systemic circuit, we're subbing out these things, right, to get our difference in pressure. It's our mean arterial pressure, so that's the aorta, minus our pressure in the veins, which we abbreviate CVP for central venous pressure. Okay, so that's just the blood coming back to the heart. Now I'm actually going to draw out the system and compare it to our pulmonary circuit. So I'm going to pull up a whiteboard real quick. Okay, so what we were just talking about, right? We have our heart. We have, I use the text boxes because my handwriting is not the best. So we have our right atrium. We have our right ventricle. Then we're going to have our left atrium and left ventricle on the left side. Left atrium, left ventricle. So I'm going to draw on our systemic circuit first, and then we're going to compare it to the pulmonary circuit so that we can kind of apply this. Okay, so when we're thinking about the systemic circuit, we have our aorta coming out, and this is not going to be an anatomically correct drawing. This is just showing us the circuit. So you'll see in lab that the aorta actually goes up and arches over. But for right now, this is our aorta. Go ahead and type that in. Aorta. We would then see the blood enter a capillary bed. Lots and lots of capillary beds, actually, as we see this split out. So we're going to show that capillary bed just by showing a little bit of a split. So think of this as a dense network. Then we're going to start sending blood back to the heart for oxygenation. So I'm going to turn it blue as we start to move into our veins. Okay, so that's the end of our capillary bed after we've gotten rid of our oxygen. And here's our veins coming back to the right aorta. Sorry, to the vena cava. Okay, so vena cava be here. Okay, so when we're thinking about the systemic circuit, when we want to find our difference in pressure, we take, could choose green, okay. So we're going to measure here. We're going to measure our pressure. And here the pressure we measure would be MAP, our mean arterial pressure. Okay, so MAP minus our pressure over here as we're returning to the heart, our central venous pressure, CVP. And that is going to give us the delta P that's going to create flow through the systemic circuit. So we actually could put in some numbers here because we do have a typical numbers for both MAP and for CVP. So the pressure in your aorta is usually about 88 mHg. The pressure in your vena cava is about 2. That's it. So if we then calculate out using this equation, right, our difference in pressure is going to be equal to 88 millimeters of mercury minus 2 millimeters of mercury. So we're going to get overall our driving force, that delta P, for our flow is going to be 86 millimeters of mercury. Okay, so that would be our difference in pressure here. And this is our driving force. Driving force. Okay. Now I'm going to erase some of this and we're going to compare that to what's happening in our pulmonary circuit, which we're going to think about less, but we do still want to understand. Okay. Is there an eraser tool? Yes, there is. Great. Okay. So now we're going to think about our pulmonary circuit. Rid of those two, so we have room. Okay. So for our pulmonary circuit, we have blood flow going out to the lungs from the right side of the heart, from the right ventricle. This is an artery, but I'm drawing it blue because we don't have oxygen yet. You remember that's something special about the pulmonary arteries. They're the only arteries we see that are deoxygenated blood. Okay, so we still see a capillary bed. We're going to think a lot about those capillary beds when we get to the respiratory system, but we don't have to think about what's going on there yet. And then on the other side, we have our pulmonary veins, bringing that oxygenated blood back to the heart. Okay. Awesome. Okay. So this is our pulmonary circuit. We can calculate the same things here, right? We can calculate our change in pressure, and therefore we can calculate the driving force happening here. Now, the pulmonary vein, we're going to start here. So if we put our pulmonary vein here, keep my color system the same as before. So our pulmonary vein still has a pressure, just like the central venous pressure in our vena cava of about 2 millimeters of mercury. But that right ventricle actually doesn't produce as much force as the left ventricle, right? Our left ventricle is really strong, contracts really hard. Right ventricle, not doing quite as much. Okay, so our right ventricle sending blood out to the pulmonary arteries. Okay. The pulmonary arteries have a pressure of about 16 millimeters of mercury. So I want you guys to calculate our pressure difference here. Therefore, think up our driving force and compare that to the systemic circuit. And give you a second, and then I'll type out our calculations. So we're using our equation here. Ooh, oh, can make nice lines. Slow though. So our difference in pressure is going to be our arterial pressure. So in this case, the pulmonary arteries. Minus our venous pressure. Still going to write that CVP because the number was the same. Okay. So we're going to do 16 minus 2 gives us 14. I'll put our units on it. So we can see that this difference in pressure is much less than what we got for our systemic circuit, right? So this driving force here, this is our driving force for the pulmonary circuit. But we know that all the blood has to go through the lungs, right? We can't not send all the blood to the lungs. We can't send like half the blood to the lungs and then out to the systemic circuit. So our flow is going to be the same. So when we think about the pulmonary circuit and these differences between the pulmonary and systemic circuit, we're going to want to think back to our overall equation for bulk flow. So bulk flow, like total flow, is just telling us that we're kind of summing up all our arteries. We're not looking at one in specific. So that flow equivalent to the change in pressure over the resistance. So we can see that our systemic circuit and our pulmonary circuit had different delta P's, different driving forces, different changes in pressure. So to come up with the same flow, we're going to need to have different resistance, right? Because we want the same amount of blood going through the pulmonary circuit and then going to the systemic circuit. So we're going to talk about resistance next. Okay. Do you guys see the PowerPoint again? Just thumbs up or a nod or something. Awesome, thanks. Sorry, I know it must be annoying to get asked that all the time, but less annoying than me talking for 15 minutes without you seeing anything. Okay, so here we see some of those differences between the systemic circuit and the pulmonary circuit drawn out in pretty graph form, right? So what we're adding to this image here, right, we're looking at how pressure changes across the arteries, the arterioles, capillaries, and then coming back, the venules and the veins. We'll talk about each of those different types of blood vessels in our next PowerPoints. But when we think about the pressure, what we're going to see is that we're going to see pressure dropping across the system, basically kind of using up some of that pressure, right? So our pressure starts high in the arteries, drops a bunch in the arterioles, continues to drop in the capillaries, And our pressure is pretty low in the veins, but there's still a difference in pressure between the beginning of our venules and the veins as they return to the heart. So for the systemic circuit, we had a big pressure difference. So we can see that this is a really big drop, right? That part in the arterioles especially is quite a steep slope. But we still see differences in the pulmonary circuit as well. Because if this line were ever flat, right, if we had no difference in pressure, there would be no flow at all, right? So if we just had a straight line from arteries to veins, kept the pressure the same, our blood would not be able to flow through the body. Okay, so this difference in pressure is important. The difference in pressure is bigger in the systemic circuit. Here's probably where I intended to draw that picture I drew earlier, but that's fine. Move forward. Okay. So now we need to think about the resistance, right? So that's the delta P part, the difference in pressure. But we also have to factor in the resistance as we're thinking about our full equation for flow, right? As we're thinking about flow, equivalent to difference in pressure divided by resistance. Okay. So our pressure gradient in the systemic circuit we just saw is much greater than the pressure gradient in the pulmonary circuit, but all our blood is flowing through the pulmonary circuit and then in series through the systemic circuit. So our flow has to be the same. The way we do that, so that when we have this equation, right, if we have high delta P in the systemic circuit, right, we divide that number by something, right? So we divide it by a resistance. So in order to get the same flow, we're going to see high resistance in the systemic circuit. So I'm going to label this. Hopefully your notes look prettier than what I'm drawing, but if they don't, you know, this will work. So this is our systemic circuit versus in our pulmonary circuit. We want the same flow. So we're going to have low delta P. So this is a small number, but we're also going to divide it by a low resistance. So a low R, so that we can come out with the same number for our flow. So that's how we're going to do that, to make sure all our blood gets through both. Okay. So the way we can change resistance, finally getting back to that question of how would we know that our resistance is the same or different? And we also have an equation for resistance. So don't really know how to pronounce it, but this is Pucel's law. It's French, don't speak French. But our resistance is going to be dependent on some constants. We have an 8. We've got an lowercase eta, a Greek letter, for the viscosity of the fluid. And then the parts that we can actually think about more are length divided by pi. And then another R. This one is the radius of our vessel to the 4th power. So our factors that are affecting the resistance to flow, right, that are in our equation, right? So flow, delta P divided by R. In order to change that R and make it higher and lower, we could change any of these things, right? Change the radius of the vessel, could change the length of the vessel, or the viscosity of the fluid. In reality, when we're thinking about the cardiovascular system, length of your arteries doesn't really change, right? Like your radial artery, for example, it's not going to get super long 1 minute and then super short the next, right? Like it has to go down your whole arm and not past your arm. So we're not really going to be paying much attention to changes in the length of vessel or to changes in the viscosity of the fluid. We're going to assume that blood viscosity is pretty constant. Blood viscosity is dependent on the amount of red blood cells. So in the long term, it could change, say if you start living at a really high altitude or something. But in the short term, we're not going to be changing the viscosity of the blood. So we can think of these as pretty invariant. But we will see that we are able to change the radius of the vessel. So mainly when we're thinking about changes or differences in resistance, I want you to be thinking here about number 1, right? This is the most important part. All right, radius of the vessel, super important. Now, the way that radius of the vessel affects our resistance, according to this equation, right? If we have, I'm gonna blow 2 straws, right? I think you can see the straws if you're looking at my face. If not, just imagine 2 straws. One little skinny straw, really low radius. One big straw, really wide radius. Think of like a coffee straw versus a regular straw, or a straw for drinking boba or something, right? You blow through one, blow through the little one, it's pretty hard. Blow through the big one, super easy, right? So the reason for that is that when we change the radius of the vessel, if we make that vessel larger, if we increase the radius or we increase the diameter, right? Because the diameter, in case you see that word later, right? I think it does appear. The diameter is just twice the radius, okay? So if we increase the radius or increase the diameter, we are going to be decreasing resistance, right? If we shrink our vessels, right, if we constrict them, if we make them really narrow, if we decrease that radius, we're going to be raising resistance. So this is going to be the main source of changes to resistance as we are looking at blood flow. And the way I like to think of this partially is kind of about the amount of wall we have. Because when we're thinking about this resistance to flow, really we're kind of thinking about friction kind of dragging on the blood that's flowing through it. So if we make our vessel wider, right, if we increase the radius, increase the diameter, then there's a lot of room there, right, in the central part of that blood vessel where that blood isn't touching the walls, so there's not much friction, so it can keep flowing past unimpeded. Whereas if we have a really narrow vessel, lots of blood is touching the walls, so lots of it is impeded by friction. Now that part's not in your textbook, but that just kind of helps me remember these things. Okay. Cool. Okay, so resistance, really all about radius of the vessel when we're thinking about blood flow. Okay. A thing that we could then notice from that equation, and do a little bit of typing. So our original equation there was resistance is equivalent to 8 lowercase eta, that was our viscosity, L was our length, divided by pi times r, our radius, to the 4th power. Right, so that was our original equation. So R equals resistance, eta, which I just typed as an N because I don't have a Greek keyboard, is viscosity, L equivalent to length. I'll make this wider for us. R is our radius. We've seen this R for resistance before, right? So we had our equation flow equivalent to delta P divided by R for resistance. So we could actually sub in this equation, get an overall equation for flow that includes our radius directly, right? So that size of the vessel directly. So if we were to sub them in, do some drawing. All right, so flow is delta P divided by resistance. But we're going to put our whole resistance equation here on the bottom. 8 eta L divided by pi r to the 4th. We could then do some nice shimmying around of our numbers, right? We would get that flow is also equivalent to delta P times pi r to the fourth. All right, so we move this up to the top, divided by 8 eta length. What you might also notice here, right, so that we have all those constants and things we don't really care about in terms of physiology on the bottom here. So this is kind of helpful that all the things we are going to be thinking about are here on the top. All right, so now we can immediately relate flow to our difference in pressure and the size of the vessel, right? So here we can immediately, maybe more obviously, see that as we raise our radius, right, make that vessel wider, that would also raise the flow, and the opposite. If we lower our radius, we'd lower the flow. Okay. So this is really the factor we're going to be changing as we start to think about the vasculature. Okay. So here we can see that in terms of our columns, right? So this is how we would tell the resistance was different when we're looking at those hydrostatic columns. Hydrostatic means a column of water, basically. Okay, so we have our two columns. We see a difference in pressure of 40 millimeters of mercury. So that's going to be the same for both A and B. That's just due to the height of these columns. We don't care how far up these tubes are, because so long as they're at the same height here, that difference above them is going to be the same, even though the absolute pressure at A and B wouldn't be the same. Okay, so both of these have a delta P of 40. But what we can see is that tube A is much wider than tube B, right? That diameter is greater, which means our radius is greater. So as that radius increases, that means our flow increases. When we look at B, we have a narrow little tube, so that radius is small, which means that our flow is small, even though we have that same delta P. This is because we changed the resistance, right? We have high resistance here for B. We have low resistance here for A due to the difference in the thickness of that tube, in the radius, the diameter of that tube. So low resistance for A, high resistance for B means that in our low resistance tube, we have faster flow than in our high resistance tube. Okay. So when we're thinking about resistance, we're mainly going to think about the resistance in the arterioles. So when we saw that graph of pressure changes in the systemic circuit, we saw that there was a really precipitous drop in the arterioles. And the arterioles is also where we're going to be doing a lot of modulation, a lot of control of radius, and therefore control of resistance. So when we think about those arterioles and we think about changes to the resistance, when we have vasoconstriction, right, we have this constriction of vaso, right? Vaso is the vasculature. So when we constrict it, we decrease the radius, we make them smaller, which means we increase the resistance according to that radius equation, that resistance equation. Vasodilation, right? When we dilate the vasculature, we expand it, we make the diameter wider. We have an increased radius, which means we're going to see a decreased resistance. So we're going to see less resistance. We looked at the pulmonary circuit, right? And we were a little puzzled by the fact that all the blood flow had to go through our pulmonary circuit, but it had a really low difference in pressure, right? A really low delta P. We understand now that that is because that low pressure gradient is paired with low resistance. So basically like wider blood vessels. And also they don't have to go as far. Those lungs are really close, right? Okay, so less resistance than the systemic circuit when we are thinking about our pulmonary circuit. Okay, I see that we're at the end of the class period, and I know some of you guys have places to go, so we'll pick up here on Monday. And those of you who haven't gotten into mastering A&P yet, go ahead and do that, get that done. I'll stick around for questions after, but you don't have to stay if you don't have questions.
Thank you.
Yep, take care.